Welcome back to IT Pro Guide. My name is Mohammed Niaz. In my previous video, we built a simple AI model using a single neuron to predict the house prices. That model was very easy to understand because it's just one input layer, that is the size, then one neuron and one output. But today we are taking a much bigger step. We're going from a single neuron to an entire neural network. Before we write any code on this, it's important, I think, to understand why one neuron is not enough for real world problems. Like we did the house price with one neuron, it's not enough for real world problems. And this video will show you the exact reason, both mathematically and visually. And then we will build our first real multi-neuron neural network using PyTorch and Python. In this video, we will first understand the limitations of a single neuron. We will discuss linear separability and why certain patterns cannot be learned with just one neuron. Then we will see how stacking multiple neuron and multiple layers helps us our model to be able to learn such a complicated or non-linear relationships. And finally, we will build a real multi-layer neural network in PyTorch to demonstrate everything we learned in this video. Before we build a larger neural network, we need to understand the core limitation of a single neuron. A single neuron is a linear model. That means mathematically, it computes a weighted sum of inputs like y is equal to w1 x1 plus w2 x2 plus b. This means it can only learn a straight line decision boundaries. If your data can be separated by straight line like this, then the single neuron works very well. But the moment your data become non-linear, then the decision boundary needs a curve or a bend. A single neuron simply cannot learn it. This is why the real world problems like medical diagnosis or fraud detection, image classifications cannot be solved with just a single neuron. The patterns are too complex and too non-linear. If you still didn't understand why a neural network need multiple neurons, then it's better we talk about linear separability. So linear separability means that two classes can be perfectly separated by a single straight line. So here in the equation you see there are two classes given. The output which is greater than 0 and output which are less than 0. So class A and class B. So these two classes are separated by a straight line, class A and class B. Then this is called linear separability with a clear straight boundary. But if you cannot draw a single straight line that separate the data, then the problem is not linear separability and where we need multiple neuron. We can use AND gate as a perfect example to show the linear separability. So x1 and x2 are the input and O is the output. For 1 1, the AND gate give one output, 0 1 is 0, 1 0 is 0, 0 0 is 0. Now let's plot this in a graph. So here is the x1, here is the x2, and here is these are the points that comes 0, and here you get 1. Now if you want to separate it by a line, yes, you can separate it by a line. So in this case, this one will work with the single neuron because it is linearly separable. So this is a very simple linear model example that you can relate. Now let's try to understand what is not linearly separable. So what is not linearly separable? What is not linearly separable means you're not able to separate the class A and class B with a straight line. Let's take the case of an XOR, and the 1 1 is 0, same input it is 0, and different input, the output is 1, same input again 0. If we plot this value, you will get like this. Now you're not able to linearly separate it with a single straight line. See, because as you can see that you cannot separate the class A and class B. That means XOR you cannot solve with the single neuron. Now let's see how we can process the XOR in a neural network. It is no more a single neural network. There are multiple neurons and there are different layers also. As you can see here, input layer, hidden layer, and output layer. Let's add the input x1 and x2. So x1 and x2 can be 0, 1, 1, 0, 0, 0, and 1, 1. Then hidden layers, you can call it as h1 and h2, and output layer, we can call it O. So here, one thing I would like to explain here is each neuron will have 2 steps. You can call it as output and activated output. So Z1, H1 and Z2, H2. Inside every neuron, there are really 2 steps. First, we compute Z, that is equal to Wx plus B. That is just a weighted sum of the input plus bias. And this part is linear. Then we pass the Z through an activation function like a sigmoid or tanh, and there you get the H, and the H is the actual output of the neuron, and this will be passing as an input to the neuron in the next layer. There are many activation functions you can use, sigmoid activation or tanh activation. In this XOR neural network processing, we're going to use a sigmoid function, and the equation of sigmoid is like this. You can say 1 by 1 plus e raised to minus x. So h is equal to sigmoid of z, that is equal to 1 by 1 plus e raised to minus x, and the output will be between 0 to 1. So whatever the score that you get in Z, it will be squashed to a number into a range between 0 and 1. Now let's continue with our neural network, and now let's add the weight. So in the real processing, the machine will guess the weight. So here we're going to manually write the weight. So here it is W11, W12, W21 and W22, and the value that we're going to give is 0.80. 1, 2 we're going to give minus 0.60, 21 is minus 0.40, and 22 is 0.90. The bias is 0.20 and the bias here is 0.10. Now let's calculate the Z1. So Z1, the formula is W11 into X1 plus W12 into X2 plus bias, that is equal to 0.80 into 1 plus the X2 is 0, so we don't need to calculate it, and B is 0.10, that is equal to 0.90. So we got Z1 as 0.90. Now we need to find out the H. So the way to find out H is using the sigmoid function, that is 1 by 1 plus e raised to minus, the output is 0.90. If you calculate this value, you get 0.710. So we can write this as 0.710. Now we need to find out Z2 and H2. So let's remove this. Now calculating the Z2, that is equal to W12 X1 plus W22 X2 plus B2, that is equal to W12 is minus 0.60 into 1. W22 is 0.90, but X2 is already, we know it's 0, so it's 0. Then the bias is 0.20. So that is equal to minus 0.40. Now we need to calculate the activated value, that is equal to sigma of, so the activated value H2 is equal to sigma of Z2, that is equal to 1 by 1 plus e raised to minus 0.40, that is 0.401. So we got the value 0.401. Now the H1 and H2 will go as an input to the output layer. Now let's calculate the output layer. So output layer also will have a bias, that is 0.05. Then let's also split this. When you split it, you have the row score Z. Then also you have the final output, that is a predicted value. So we write this, and the predicted y is going to be the sigmoid of Z, that is the activation function. So now we need to calculate this. So we have to also guess the weight for this. So the weight we can put 0.70 here, and here 0.50 minus, and bias we already have. So let's calculate it. Now let's calculate Z. So Z is going to be H1, then W1, let's put 1 W1 plus H2 W2 plus bias. H1 is 0.710 into weight is 0.70 plus H2 is 0.401 we have here, into weight is minus 0.50 plus the bias is also 0.05. That's going to give you a final value of 0.3465. So let's only keep the output, that is Z is equal to 0.3465. Now how to get the Y? That is the predicted value in the sigmoid of the output, that is 0.3465 is equal to 1 by 1 plus e raised to minus 0.3465. The output of this is 585. So your output, since this is range in between 0 and 1, anything greater than 0.5 is predict as class 1. So here the output predict as class 1, and that is the output of XOR. If you pass 1 0 through an XOR, the output is 1. We were solving the XOR function manually using the neural network. Now we are going to build a small neural network in PyTorch that actually learns the same XOR function. So first thing, we need to create the data set. Here the data set, so 0 0 0 1 1 0 and 1 1. Then the expected output, so for the same input we get 0, and for different input we get 1. Once you define the data set, the next step is to build a neural network. So if you look at the picture here, you can see we have initially 2 inputs and 2 outputs. So that is the X1 and X2. Then outputs are H1 and H2. That is what we written here. In the first layer in the model, input features are 2, that is X1 and X2. Output features are also 2, that is H1 and H2. The second layer only have 1 output, but it will have 2 input features. Then we were using sigmoid for the as the activation function. As I explained, that the neuron have two steps. So the activation function, we use sigmoid because the value, the answers we are expecting either 0 or 1. So we have to sketch the answer in between 0 and 1. That's why we were using sigmoid. So that is how the model is. Then the forward propagation. So this is how we predict the y. So we have two layers. The first layer is H1 and H2. So here you can see, first we calculate the raw value, then we calculate the H1, and that is what you can see here. So H is calculated from the first layer. Then the output, the y predicted, is calculated from the second layer. And here you can see the input is given as the output of the first neuron. Then we return this value. Now let's create the model. So whatever we defined here, we created here. Then we have to define the loss function. So we're going to use binary cross entropy as a loss function. Then we use the gradient descent. So here in the gradient descent, you can see we pass the model parameters. Then the learning rate is 0.1. Then we also define here momentum. So this will help to avoid these zigzag gradient results. So this will give a learning a smoothness in the learning process. Then we reach to the training loop, and I'm going to use 5000 loop. We call the model, and this is the predicted output. Once we get the predicted output, we compute the loss. That is the second process, right? We compute the loss, and if the loss is high, then we do the backward propagation. So here you can see that we are clearing the previous gradients. Then after that, we do the backward propagation. Then we update the weights. Here it print the progress. So once we completed the training model, we can just try what the actual value that we are getting when we feed this model with 1 and 0. So now let's run this. So here you can see the loss is going less. Once it reached to 5000, the loss is really less. And here you can see that it predicted the XOR result with the model that we created as same input. It predicted 0, and different input it predicted 1. So our training is successful, and our model is predicting the XOR values clearly. And that brings us to the end of this tutorial. We started with the idea of linear separability. We understood why a single neuron cannot solve XOR, and we learned how multiple neurons and nonlinear activations make neural networks so powerful. Then we build the XOR network step by step by manually calculating Z, H, and applying the functions. And finally, we let PyTorch model to learn the XOR function completely by its own. So thank you so much for watching. If you enjoyed this tutorial, please like the video, subscribe to the channel, and check out my courses on Udemy. I will see you in the next video.